Good morning, students. In the previous lectures, we have solved the analysis problem on bolted connections, especially one problem on lap joint and one more problem on butt joint with different conditions. Now, in this session, we will solve the design problems. So, two design problems. One problem is on lap joint and another problem is on butt joint. So in this session you will come to know that how to design a bolted connection joint, simple bolted connection joints. So first one we will solve the lap joint problem. So that is problem number 3. It is like this: design lap joint between plates 100 into 8 mm so as to transmit a factored load of 100 kN using a black bolts of 16 mm diameter grade 4.6. The plates are made of grade Fe410. Find the efficiency of the joint. So as usual, the first step is to write down all the given data. So factored load, it is given as 100 kN and the grade of the bolt is given as 4.6. Diameter of the bolt D is equal to 16 mm. Fu, that is ultimate tensile stress of the plate material, is 410 MPa. As the grade of the bolts is given as 4.6, so we can calculate the ultimate tensile stress of the bolt as 400 MPa. So the partial safety factors gamma MB and gamma ML, so these have to be taken from the table 5 of page number 30 of IS 800 2007. So the first diagram I have shown here, lap joint, simple. So one over the other plates. The size of the plate is also given. So it is a lap joint. The bolts will be in single shear and bearing. So first we will calculate the bolt value. So for that, first step is to calculate the strength of bolt in single shear. So again go to the page number 75, clause number 10.3.3 of IS 800 2007. Nominal shear capacity of bolt, that is phi NSB is equal to Fu upon root 3 in bracket NN A and B plus NS ASB. Then we will again assume here, that is NN. NN means the number of shear planes falling in the threaded area, and NS is number of shear planes falling in the shunt area. So this is a lap joint. We will assume that the shear plane is going to fall in the threaded portion. So we will take NN as 1 because there will be only one shear plane, and NS will be 0. A and B is equal to 0.78 times pi by 4 into d square. So substitute the value of diameter of the bolt. So we get A and B as 156.82 mm square. So substitute this value in the formula. Phi NSB is equal to 400 divided by root 3, 1 into A and B, plus as NS is 0, substitute 0 into ASB. So phi NSB we are going to get 36217.9 Newton. So convert it to kilonewton by multiplying into 10 raised to minus 3. Then to get the shear capacity of the bolt, that is design shear capacity of a bolt, so divide the VNSB, that is nominal shear capacity of the bolt, by the factor of safety. The factor of safety is 1.25. So we are going to get design shear capacity of a bolt as 28.98 kilonewton. Then the next step is to calculate the strength of bolt in bearing. Again, we'll go to the page number 75, clause number 10.3.4 of IS 800-2007. The nominal bearing strength of a bolt is given by NPB is equal to 2.5 into KB into D into T into FU. So again, the KB is smaller of E upon 3D naught, P upon 3D naught minus 0.25, FU by FUB divided by FU and 1. So among all these values, we have to take the smallest value. So again, by referring the code book, D naught, that is the diameter of the hole, equals to 60, that is the diameter of the bolt, plus 2 mm, that is for clearance. So we will get 18 mm. So we will get from the code book by using the values of 2 mm. So D naught is equal to 18 mm. Then again, we refer the code book. P, that is pitch. So minimum pitch value is 2.5 times the diameter of the bolt. So we are going to get it as 45 mm. So end distance, or it may be edge distance, it is 1.5 times diameter of the bolt hole. So we will get end distance as 25 mm. So substitute these values, that is D naught, P and E, in these values, in these formulas. So we are going to get E upon 3D naught as 0.5, P upon 3D naught minus 0.25 equals to 0.58. So FUB by FU is 0.975 and one more is 1. So among these 4 values, so this is 0.5 and this is 0.58, this is 0.975 and this is 1. So among these 4, we will take the smallest value, that is 0.5. So KB is equal to 0.5. So now you substitute the value of KB 0.5 in the nominal bearing strength of the plate. So after substituting, you will get 2.5 into 0.5 into 60, that is diameter of the bolt, and T, it is thickness of the plate, 8 mm, and FU is 410. So you will get 65,600 Newton. So convert it to kilonewton by multiplying 10 raised to minus 3. So you get 65.60 kilonewton. Then, so design bearing strength of a bolt is VDPB equals to VNPB divided by gamma MB. That is, nominal bearing strength is divided by the factor of safety 1.25. So we get 52.48 kilonewton. Next, the strength of the bolt will be minimum of the strength in shear and bearing, that is 28.98 kilonewton. So in the bearing we got 52.48 kilonewton, and in the shear we get it 28.9. So among these two values, that is 28.98 and 52.48, we have 28.98 kilometer. And this value is called as bolt value, that is 28.98 kilometer. So now we will calculate the number of bolts required, that is calculated factored load divided by the bolt value. So factored load is given as 100 kilonewton and bolt value we get from the calculation as 28.98 kilonewton. So we get the number of bolts required as 3.45. So as we know, we cannot provide in decimals. So make it as 4, say 4 bolts. So required number of bolts are 4. Next is detailing. You can see here the detailing. Minimum spacing from the calculation we got as 45 mm. Minimum edge distance as 27 mm. And the number of bolts are 4. And if you see the cross section, it is like this, and plan it is like this. So you can see in the plan, here one bolt, 2, that is one line of bolt, and another line of bolt here. So totally 4 number of bolts, and these are 2 line of bolts. Total 4 number of bolts, and the bolt lines are 2, and the pitch, that is 45 mm. So we have used here whatever we get from the calculations minimum values. So here you can see minimum edge distance is 27 mm. That is we got it from the calculation. But if you want to make it more, say about 30 mm, you can also have the choice. You can make it as a designer. You can make it as 30. But from the calculations we got 27. That is a minimum edge distance. So less than this value, like 25, you cannot, 26, you cannot provide. But you can go for higher value. 27 is we got. So you can make it as 30 if you want. But we have taken the same value. So you can see here 27 mm the edge distance and 45 as the pitch, that is the center to center distance between the bolt lines. You can see this is pitch. So this is edge distance, and the width of the plate is given as 100 mm here, this one. So this is written here 100 mm, and the thickness here, this plate thickness is 8 mm. So in the calculations you can provide. So this is the, you can see the detailing. So in this direction, this is the force line direction you can call. So this direction, that is perpendicular to the load, I have provided a 27 mm as the edge distance and 27 mm as edge distance, and remaining, that is 46 mm. So from this to this I have provided 26 mm. So this one is generally called as gauge length, and this is pitch length. This distance which was shown here in the direction, and in this direction it is called as gauge distance, and here it is edge distance or end distance. Here also. So this is about the problem number 2. Then we will go for the another problem that is based on the butt joint. So in this case, if you see the problem statement, that is find the efficiency of the joint. So the efficiency of the joint I have explained in the previous problem, that is in problem number 2. In the last problem, I have explained how to calculate the efficiency. So again, I am not going to solve here, but there are 2 methods to find out the efficiency of the joint. One is to calculate the efficiency per pitch length, and another one is to calculate the efficiency for the total joint. So you can use any one method, you will get the same answer. So we'll move on to the next problem. So its statement is like this: two ISF sections 200 into 10 mm each, 1.5 meter long, are to be jointed to make a member length of 3 meter. Design a butt joint with the bolts arranged in diamond pattern. The flats are supposed to carry a factor tensile force of 450 kN. Steel is of grade Fe410. 20 mm diameter bolts of grade 4.6 are used to make the connection. So again, in the solution part, the first step is to write down the given data. So grade of the bolt is given as 4.6, and the diameter of the bolt here is given as 20 mm, and ultimate tensile stress for the plate is 410, and for the bolts is also for 400 MPa, as grade is 4.6 here. Then partial safety factors, again you can refer the table number 5 of page 30 of IS 2007, that is gamma MB and gamma M requirement. And ISF sections. ISF means Indian Standard Flat Sections. Okay. The width is 200 mm and thickness is 10 mm. Okay. Then we will assume it is asked us to design a butt joint. Okay. So we know that there may be single cover butt joint or double cover butt joint. So if we go for a double cover butt joint, the rigidity will be more and also the efficiency will be more compared to the single cover butt joint. So now we will assume we will provide a double cover joint. So as usual step, we will calculate the bolt value as in the previous problem. We have calculated the bolt value. Here also we will calculate the bolt value, that is the strength of the bolt. So again, the step to calculate the strength of the bolt in shear. So again, it's a repetition. You can see here, page number 75, clause 10.3.3 of IS 800 2007, and the formula is VNSB is equal to FU by root 3 with the bracket NN A and B plus NS ASB. So in this case, as it is a double cover butt joint, you can see there will be two planes, two shear planes. Again, I am going to assume the two shear planes are going to fall in the threaded area, not in the shank area. And you can also assume one plane in threaded portion and another plane in the shank portion. It is left to, there is no problem. But I have assumed here the two planes in the threaded area. So NN will be equal to 2, then we'll get A and B as 245 mm square. Okay, A and B. Then you substitute this value NN equal to 2, NS equal to 0, and A and B is 245 in this equation. So we will get VNSB as 113.8 kN. That is nominal shear capacity of a bolt. So you can, next step is to make it the design shear capacity of a bolt by dividing it from the factor of safety. We will get 90.54 kN. So we get 90.54 as the design shear capacity of a bolt. That's double shear. So next step is to calculate the strength of bolt in bearing. Again, you go to the page number 75. Here the formula is VNTP is equal to 2.5 kb dTFU. So kb, here kb is smaller of these things. I think it is a repetition. So D naught, that is the diameter of the hole, you get 22 mm. So pitch as 50 mm and end distance 33 mm. So if you multiply end distance, you are going to calculate 1.5 times this D naught. So 1.5 into 22, and pitch you are going to calculate 2.5 times that is the diameter. So 2.5 to 20 will get which as 50 mm. So substitute di naught P young distance C in these formulas. So we will get the kb as 0.50. So substitute all these values in the kb, t, t, f. So if you look into the here, VNPB is equal to 2.5 into 0.5 into 20 into 10 into 410. So you get 102 500 Newton. So convert it to kilonewton. So you get 102.5 kilonewton. So again make that one design bearing strength by dividing it by the factor of safety. We will get 82 kilonewton. So again the bolt value is the lesser among the shear and the bearing. So we have the design bearing strength value as 82 kilonewton and here design shear capacity of bolt is 90.54. So among these two the least value is, you can see here how much it is, 82 kilonewton. So number of bolts required, load divided by bolt value. 10 that is equal to 5.48. Say it as 6 bolts. Right? 6 bolts. So next is as it is a double cover joint, and one more thing asked in the problem is you have to provide the bolts in diamond pattern. So double cover butt joint, we need the cover plate. So the thickness of cover plate is like this. So it should not be less than 5 by 8 times the thickness of the plate. So the thickness of the plate, that is here 10 mm. So 5 by 8 into 10, it is 6.2, it is coming. So it is nearly 8 mm, make it as 8 mm. So provide 8 mm thick cover plates to make a double cover butt joint. And the detailing or diagram will be like this. You can see here 1, 2, 3, 4, 5 and 6. 1 bolt here, 1 bolt here, 1 here. So 6 number of bolts which are in, you can see it is in the diamond pattern, and here it is a, you can see it is a dotted first bolt line, second bolt line here, third bolt line, it is shown here like this, and 2 cover plates which are of 8 mm thickness, and this is 10 mm ISF plates or flats, you can see. So this is the detailing. So you solve this problem by hand and detail it by the hand by showing the edge distance, pitch distance, whatever you have calculated. So this completes the problem number 2. Means problem number 4. That's problem number 2 in the design, but overall it is problem number 4. So these two are the problems. One is a lap joint, another one is a butt joint. So in the next session, I am going to take the design of the high strength friction gauge bolts.